is used for simplification. So these are the examples which we'll look at today. Let's start off with the first one. And previously we discussed what a perfect square is. Essentially it's when you have some value to the power of 2, which you can of course expand as a plus b multiplied by a plus b. So this is what we mean by a perfect square, and there's just a few different ways to treat algebraic equations when factorizing, when you may result in a perfect square. So that's what we're going to have a look at today. So with this first example, x squared plus 2xy plus y squared, a good technique is to often split out this middle term. So let's give that a go. So let's split 2xy into xy plus xy, and let's leave x squared and y squared as is. And what does that leave us with? Well, it leaves us with 4 terms. Let's group them into 2 lots, and let's take a common factor out of the first. So here we can take an x out, and that leaves us with x plus y. And similarly, we can take out a y out of the second set of brackets, which leaves us with x plus y. And then, as you would have seen previously, by grouping the common brackets, or by taking the common set of brackets out of this equation, we're left with x plus y multiplied by x plus y, which of course gives us our x plus y all squared. So that's one way to approach an equation where you may result in perfect squares, is to attempt splitting out the middle components. So let's have a look at another example now. The second one, which was x squared minus 4x plus 4. And in a previous video we went through a technique where you find 2 numbers that add up to give this middle term, and 2 numbers that multiply together to give this end term. And in this case, we can look at the factors of 4, the factor pairs. We've got 1 and 4, which doesn't really help us, but we've got 2 and 2, or in this case, -2 and -2, which do indeed help us. So here we're left with x minus 2, which minus 2x minus 2x gives us negative 4x, and minus 2 multiplied by minus 2 gives us positive 4x, and in fact it is correct and leaves us with x minus 2 all squared. And that's our solution for the second question. And let's have a look at our third question. 9x squared minus 12x plus 4. So one other interesting technique is to attempt to rewrite each component in a bit of a different way. So let's write 9x squared as 3x all squared, and let's write, like we did previously, 12x as split into 2 components, so minus 6x minus 6x, and then we'll also represent 4 as 2 squared. So now, if we were to have a look how we had a previous equation, this is kind of our x value, this is kind of our y value, and what in the middle we need to see is if we can have some combination of x and y. So let's have a look. If we're trying to write our equation in the form here, in this case our x is 3x and our y is 2. Now it's just a matter of trial and error. Let's see if putting some value here will result in negative 6x or minus 12x as it ends up being. But we should think about each of these as a single component, so that we're essentially trying to get negative 6x twice because of the squaring. So we know that the sign has to be the same in each equation. So let's attempt first, we know that we're looking for minus 12 or minus 6 within each, and we're also looking for plus 4 as a resultant. So if we're looking for plus 4 at the end, it means that we must have either 2 positive values or 2 negative values. But because we have negatives within the equation, indicates that we must have 2 negatives. So that's why we're inclined to think that this might be our solution. And of course, what we can do here is 3x minus 2 all squared. We can write it like this, but to verify whether we're correct here, we can expand using our distributive law that we've used previously. And what do we end up with? We end up with 3x multiplied by 3x plus negative 2 multiplied by 3x plus negative 2 multiplied by 3x, and then minus, plus negative 2, negative 2. And if we expand this all out, we end up with 9x squared minus 6x plus 4. So we do indeed get the answer we're expecting, which is, if we go one step further, exactly the same as our original equation. So therefore we know that this factorization is indeed correct. And as I mentioned, all of these examples were just the resultant answer was just a perfect square. So you can see a few different circumstances and cases when you might end up in a perfect square. And it's a good idea to practice a few of these so you might recognize them and sort of jump ahead a little bit faster rather than going through the full process. But that's pretty much it, guys. Thanks for watching. Hope you enjoyed, and I'll catch you next time.